Section, the first major topic before we get into the actual science and math of engineering is what is engineering physically. So we're going to cover a few objectives here. But before I even get into those objectives, based on your reading last night, pages 5 through 11, for those that had the right what do you think in your own words is engineering? Physically, what would you say in your own words is engineering, or examples of engineering, something that's involved? Right. Application of science and math, okay?
It's like you're given a problem, you have to find something, and you use like different areas of science, like electrical, mechanical, chemical, and you they're all connected, and you use them to solve one problem.
Yeah, you give it it's problem solving in its advanced stages. Math and science, applying math and science to a complex problem, and then interdisciplinary work that's involved. And that's the first thing you probably saw when you were reading through 5 through 11. One of the big things is that you work in groups a lot as an engineer. Now, if you don't plan on being an engineer, it doesn't mean that what you're learning here is not going to help you, depending on what job you have. You're going to probably work hand in hand with engineers all the time. If you're in a business field, you're going to constantly work with engineers. Maybe you're a consultant that works with engineers. Maybe you work for New York City, some public office for New York City. Well, you're always going to be working with engineers, with public jobs and public works, all different things. So the biggest thing about engineering is that it's everywhere around you. It's everywhere around you. There was also a part in your book, I think it was like the first section or the first part of the chapter that said, when you wake up in the morning, look around you. Try and look at things around you and figure out and say to yourself, everything around you involves engineering. Think about how. How that is like this table, obviously. To build anything involves some form of engineering. Anything electronic around you, literally, that exists involves some form of engineering. So it's everywhere. That's the whole idea. And that's why you hear people all the time talk about, when they talk about job security, when you're younger, and you hear about jobs that there'll always be need for things, you always hear there's jobs for nurses, doctors and nurses, the medical field. You always hear there are jobs for engineering. Why are there always jobs for engineering? What do we constantly want to be doing in life?
Evolution, improvement, and innovation.
Yeah, improving things and innovating. And evolution, that works too. Yeah, you are evolving sometimes. So you want to improve on things. You want to get things better. You want to be more efficient in life. If you think about a simple company like Amazon, Amazon is an amazing example of engineering at its finest. When you think about the production line processes that go into Amazon, the packaging, the fact that it's not actually even humans that are doing it, that it's all machines that are doing this packaging, it's kind of scary actually and crazy. So you also have to consider the, not ethical dilemmas, but I guess ethical dilemmas of things like machines replacing human jobs. That's another big thing in the 21st century, and several of the few leading scientists now are scared for human existence when it comes to machines. Because machines are taking over a lot of jobs. We notice more and more that there's so much of a surge in unemployment. And a lot of the reasons for that is not just the fact that people might not be A, qualified, or B, have enough school under their belt to get that job, but those jobs are physically being replaced. So as much as engineering is awesome, and I study engineering, so I love learning about engineering, it's not always something that might help humanity. Give me an example of an engineering feat that did not help humanity at all. I can think of several. An engineering feat, something amazing in a sense, but it did not help humanity. Listen. Nuclear bomb. That's a prime example of that. Without engineering, you're not making a nuclear bomb. You need to actually have that research, the science and math that went into it. And you might argue that it helped humanity by ending a certain war and stuff, but it didn't help humanity in the sense that we're, now a much more violent race, or whatever, species rather, not race, species. What else? What's another example? Something else? Come on. You live in New York City.
You can make an argument for everything.
You can make an argument for a lot of things. Absolutely, John. That's why I said I can think of a million things. Think of something else. Come on. Try to come up with your own example. What's another thing in engineering that, in the end, somehow caused some suffering for humanity? Let's say that, instead of didn't help humanity.
I guess you can say all the new weapons that came out of World War I, tanks and machine guns and cluster gas.
any new weapons, especially I was going to go to chemical stuff. Very good. So chemical weapons. What I was thinking were chemicals. Where else are chemicals not good? Pollution is one. Okay, good. Engineering has created a ton of pollution. A ton. All the byproducts, right? What else? Where else are chemicals all the time that are not really good for you? Where? I heard it somewhere. In food. In food. I heard somebody say food. In food. Think about food all the time. Think about the rise of things like autism. A lot of different not new, but more prominent, I don't want to use the word disease. Is autism a disease? Is it considered a disease? Disability or disease, one or the other? Okay. Think about the rise in a lot of things, a lot of new ailments that people suddenly are having more and more of. Think about that. Like, where does that all come from? It's not just a matter of evolution there. There's something that's causing that. There's something that's changing the way the biological system in your body is working nowadays. So chemicals are huge. I was personally thinking also about infrastructure. Think about how many times you hear on the news of something collapsing. A building, a floor, a bridge, some sort of a structure. So yeah, engineering helped us to bridge the gaps, no pun intended, but literally bridge gaps in humanity. But also, it's not really helped us all the time when we have these disasters. So today we're also going to take a minute and look at not only accomplishments, but some failures. Why is it important that you need to look at failures? To see how to improve, not to repeat it, to learn from it. Good, all good answers. You have to. If you don't, it doesn't make any sense. Make the same bridge that failed in the past, it's going to fail again. Even if it was some extenuating circumstance. Tacoma Narrows, we'll talk about at some point in this lecture. How many people know about Tacoma Narrows? You know of it? Okay, so that's good, actually. So we'll talk about Tacoma Narrows, but it was a bridge. Yeah. And it happened to fail in this very, very particular state. All the conditions needed to be perfectly right for this bridge to fail. But one day, all those conditions were met, and that bridge failed. So they learned from that. They didn't build a bridge in the same fashion, or maybe they reinforced part of it. Anybody been following the New World Trade Center construction? Whatever it's called? Do you know about the improvements in civil engineering they've been doing? Yeah. You know what I talked about, maybe one or two of the things you've read about or know about?
The first,
an example?
50 feet has a solid core.
Which in the past it did not. What was the core made out of in the old ones? Anyone know?
Steel.
It's all steel.
Yeah.
And what happened? Yeah, the jet fuel caused a lot of that to melt, and which is what really ended up causing the collapse. So what is it? First, how much of it?
Like 40 feet. 50
Okay.
feet. It's like basically if you run up the building, you can't knock it down. Like any bomb tapped to your chest.
It's like unbelievable. I mean, and obviously, after what happened, not only are they trying to make it better, but they're trying to make it indestructible in a sense, right? And that's the whole concept there. So you have to learn from those mistakes. Pete?
Is this like another building you're building, or is this
No, the new one that's built. Yeah, it's called the Freedom Tower? Thank you. Sorry, the Freedom Tower.
One world trade.
One.
Working on like construction, is that, are there still?
I think it's done, right?
Yeah.
Pretty sure it's like completely finalized now, yeah. Yep. Johnny?
What is the core method?
Don't know. Well, just thinking, right, outside the box. I really have not read about this, but just using logic. I'm thinking it's going to be part of concrete for sure. Because you're going to notice concrete's not going to melt. Even high enough temperatures, you're not going to have problems with concrete melting before it gets like scorched and weakened. I'm guessing there's probably also steel still, some sort of reinforcement. And then I'm probably guessing that there's a casing around this core that prevents certain temperatures from melting what's inside of it. Maybe it's something that prevents some sort of black box radiation that keeps out all the heat. It's probably insulated very well so that nothing would cause that to melt or fail. But I don't know. I have not read about it. But I know that they've been doing obviously a lot of improvements because of what happened.
It's the old World Trade Center had I-beams that are quarter, half-inch thick, and that's easy to melt through. But if you only steel would be a much bigger, it's not that easy to melt through.
Okay, so that they changed the geometric constraints on it. Do we know what I-beam is? So we're all familiar? An I-beam literally looks like an eye. So part of the beam is going to look like this. You've seen these structures all over. If you're walking down Lexington and they're doing all that work and you look up, you're going to see a beam and the beam comes out towards you. Imagine this is three-dimensional coming out toward the room. Okay, so the beam is literally this long, but that's the shape of it. The reason I-beams were invented, in addition to box beams and the other ones that are called, what's the third type? Right. The reason they were invented, they provide the same structural stability in forces. Like, so if you're trying to combat a certain amount of force that would affect the building or affect the structure, that a solid block would, but with how much less material. It's all about saving money, right? So all this material that might be there, if this were a solid like beam of steel, is not there. So you save a ton of money while it still resists the bending motion of the building and the twist of both. So when I took a class on solid mechanics and design, we literally looked at beams for like at least 3 or 4 weeks. The different designs, the math behind it, how you can determine exactly how much force it withstood. How much force it actually could withstand, and how much of a difference that has when compared to the actual solid beam. What else did we say a minute ago? All right, let's get into these objectives here. So we're going to talk about the progression from being like a young person who likes to build stuff to actually designing things. Talking about the branches of engineering, some historical significance, looking at some sort of, I guess we call like the fathers of engineering, then talk about some accomplishments and catastrophes in engineering itself. First, let's talk about etymology. Okay, etymology. So this Latin term really represents cleverness, or to contrive or derive or devise something. So when you're thinking about engineering, just think about the fact that when you're doing something that involves engineering, you're always designing something. Okay, and when you're in engineering, if you end up taking it in college, if you're interested in becoming an engineer, you're going to hear about the fact that it's all about the design process. Okay, it's all about the design process. And when I was a freshman as an engineer, I probably wanted to shoot my professor every time I heard that, because it's all I ever heard. Until I actually went through school for a couple years, I didn't really recognize what they were talking about. So the idea of always being able to design something and improve upon it. There's a saying, what is it? There's a saying pretty much that, you ever hear like, if it's not broke, don't fix it? Or don't reinvent the wheel kind of saying, meaning like, if there's something that already exists, don't you don't have to come up with something even better, it's already there, don't waste your time. Well, the whole concept of engineering is kind of the opposite of that, really. It's saying like, you know what? If something isn't broke, maybe it's not being used to its full capacity. We could push it to the limits a little bit more. Or if there's an item that does a good job, can I make it better? So I'm going to reinvent the wheel. And as you obviously know, many times over, people have reinvented things. What's an example of something maybe in the last 10 years that's been reinvented? Completely reinvented. Give me an example. Cell phones. Great example. I mean, think about, when I was younger, cell phones literally only had little digits on it, that was it, and they were all flip phones. Didn't even exist to have a screen on something. It was a flip phone, like little pixels and stuff, and you couldn't even see pictures, anything. So huge reinventions. What else? Computers. I mean, we're talking about going from, I don't know if you know this, but one of the first computers was bigger than this room, and a simple like electronic watch has more memory on it than a computer that big did back in the day. Incredible. Yeah.
Maybe like safety in cars.
Say again?
Safety in cars.
Yeah, absolutely. And this year, actually, we're going to talk about that for a while. We're going to talk about how they redesigned a lot of cars for safety. They moved around where the gas tanks used to be located. They moved where the seats were, because a lot of people were dying from impacts, especially side impacts. Right?
I was just saying, I don't do it for the whole.
Okay. Yeah. So there are so many things, obviously, that have been reinvented. So yes, as much as we might want to say, like, don't reinvent the wheel, as an engineer, that's kind of what you're doing all the time. You're coming up with better ideas and ways in order to help further science and technology and humanity. All right, so here's your progression. So when you're younger, as a kid, what might be some traits of someone who will become an engineer? Like, how would you recognize that your son or daughter, when you're older, might be the kind of kid who's like really going to be good at this?
Maybe like as a kid you played with Legos a lot?
Like to build things. What else? Someone who's really creative. Curious. And what? Play-Doh? Play-Doh? No, that makes sense because you're designing things. You're building artistic.
Interest in around the world. Like they take interest in seeing engineering around.
Yeah, so they're interested in advancements in engineering and things that are coming up all over the world. Absolutely. I don't know, this is another thing I'm thinking of. Have you ever met somebody who just loves to take stuff apart? Like literally, like when, I can't explain. When I was younger, I was not like super into that. I like building things and stuff, but I never got into like taking things apart. But I had friends when I was a kid, so I did this thing called, it was like a revolving doors gifted program for science and math students. And I would be in this program, and I like science and math, but I was in there with kids who, at the age of like 10, were taking apart electronics, rewiring it, figuring out how it works, just like tinkering around. So that creative nature you're going to see a lot in people and young kids who eventually become engineers. As a student, usually it's someone who's a good problem solver, who's good at math and science, who likes to think outside the box and come up with ways to have better solutions to problems that might not be solved in an optimal way. And then as a professional, there are two forms of engineering, really. Two forms: industry and education. They're both just as important. Think about it. If you don't have someone who can teach engineers, you can't have engineers. So the biggest field in engineering right now is actually professors of engineering and research. All of the new products and stuff come out of research and design. Where does the funding come from that? It comes from universities. Where does that come from? It comes from sometimes public grants, sometimes private grants. But these researchers at universities, these professors that have like a slew of 30 graduate students working for them, working in the lab, coming up with ideas, that's where a lot of your engineering applications come from. Then obviously you have professional engineers who work on a daily basis as an engineer, probably for an engineering firm, who have an engineering license, who are able to sign off on drafts for buildings, or sign off on electrical blueprints for some new structure or something else. So when it comes to a professional, you have the researcher / professor, and then you have the professional engineer that works in industry. Those two things.
Do you have like a dream job that you want, like straight out of college, or did you
Me?
did you want to teach engineering?
When I was in college, I loved learning engineering. I really did. And grad school, I absolutely loved. I never really liked research, though. So when I was in grad school, I chose the non-research option. So I took a lot of classes. I liked just learning about math and science. And then when I was graduating from grad school, I wasn't really sure I wanted to work like in an office setting as a professional engineer. So I kind of strayed away from that. And I was like, I want to stay in the like teaching area. So I entered a volunteer corps, and that's how I ended up teaching. So I didn't really ever say to myself like, oh, I want to be a teacher. It never crossed my mind when I was younger. It wasn't until I was kind of finishing up engineering that I recognized that I didn't want to be in an office doing, in a sense, it's not correctly or grammatically correct, but doing engineering every day. I had internships, and those internships were probably the worst thing I could have done, but the best thing I could have done. In a sense that they really pushed me away from engineering because I didn't like them. I had an internship at Parsons Engineering in the city, down Lower Manhattan, and then one out in Long Island, a small engineering firm, Greenman Peterson. And for 2 summers in a row, between sophomore and junior year, and between junior and senior year, I did those internships. And they didn't really utilize what I felt my capacity was. I was doing stupid stuff because I was an intern. So to me, it like morphed my view of what I'd be doing all the time. And I think it really impacted the fact that I didn't go on to be an engineer. But at the same time, there's the, you see it, you don't see it now, but now you see it. Like, I wouldn't have been a teacher, obviously, had I done that. And I do like teaching, obviously, you guys know that, or else I wouldn't still be doing it. So I don't see myself changing, but long term, I think I'm going to become a professor of college. But probably not for at least 10, 15 years. I like teaching high school. I think it's fun. It's more energetic. I'm like, I like coaching and stuff. I'm involved doing that. So, but I think like, if I one day have a family, which I hope to do and stuff, I'll go to be a professor. You get a lot more time for your family. You could then get paid to do research as a professor, as opposed to when I was a grad student, I was kind of like just being told to do research, So that's kind of what I want to do eventually. All right. Now, I don't need you to read this out loud. We don't have to read this out loud together. But what I do want you to do real quick is simply read this to yourself, please. Read through these 5 quotes of what people perceive engineering to be. Just take a minute, just read through them. You also, analyze them over overly analyze them. Should be true. So what do you notice is in common here?
Application.
Okay. Application is everything good. What else? What else? And obviously I italicized application, all of them. Design. Okay, science, math. So no matter what people conceive engineering to be, you're designing things and you're applying them to math and science. So when I was talking yesterday in my physics class for this year, they were asking about what physics is going to be like for the year, and I was trying to give them an overview. And the easiest way I was able to explain physics to them was by saying, like, you know what, you're going to take what you've learned in math and science, and you're going to apply it to real life stuff. And really what you're thinking about there is engineering. And I actually pulled this up and showed them, and I said, well, here's some definitions of engineering. It's kind of what you're doing in physics, but taking it to the next level. Okay, you don't just stop and look at theoretical stuff. Now you actually might be building stuff. You might be actually putting that to use. Okay? I was joking last year. I forget, I wasn't joking, but somebody was, and then we started joking about it. Have you ever Urban Dictionary the term engineer before? It's funny because there's some funny stuff. But then afterward, the other stuff that people talk about is pretty much what you're looking at here. So feel free, you can do it on your own if you want to, read through it real quick, because some of them are really like hysterical, what they write about what engineers are. But for the most part, even the ones that are jokes still talk about the fact that it's somebody who's going to be doing a lot of work applying math and science. All right. Yeah, some are inappropriate, so you can keep those to yourself, but some are really funny also. Okay? All right. So let's talk about, in your text, you talk about, in your letters out rather, some characteristics. Okay, some characteristics of engineering. So what does the term optimization mean? We're going to use that a lot this year. What does it mean to you if I said, you know what, you really need to optimize the situation better? What do you think I mean by optimization? First, more efficient. Okay? Well, more efficient.
Like the smallest amount of stuff that
Resources. Using a minimal amount of resources. So Victoria gave us an example of how you optimize. You minimize resources. Good. What else? What are some other examples like Victoria gave of minimization and maximization? What might you want to maximize as an engineer? Pick up this on Friday. What? Profit. Good one. Profit. We'll talk about this on Friday. So, I'm going to put up the next reading assignment under homework. Make sure you do it for Friday. 2 quizzes on Friday. One based on the first reading, one based on the second. Be ready for them, please.